Welcome to the Section 4 Reactions of Aromatic Systems Synthesis Work-Along. In this video, I'm going to go over two different, pretty difficult synthesis problems, help you understand how I like to approach synthesis problems in general, which will be useful for the final as well as the midterm, as well as how we could deal with these EAS reactions specifically. Looking at the first problem, we can see that synthesis problems are going to involve more steps. The idea is that, and you may be given some specific instructions for any question, and my instructions here are you can use any reagents you want, assuming you can't just buy this chemical. Starting from the benzene, we need to find a way to make this other final product. When approaching synthesis problems, it's useful to both think backwards and forwards. Not that you have to do both every time. Sometimes you might have success thinking forwards. Sometimes that might be difficult. You might have success thinking backwards. One idea that I really like, though, is if you think forwards and backwards one step and get, let's say, the product of the first reaction and the reactant of the last reaction. And let's say maybe you have a couple ideas of how you could get this, right? These are really simpler ABC style questions where you can use your knowledge to think of what transformations can I even make. The idea that I have is that once you have your options in front of you, any way that you can connect these products and reactants is going to be a valid synthesis, right? So let's say you try it and you realize, well, wait a minute, right? These are pretty different. They're hard to see immediately the pathway, but maybe there's a way that I can connect these. Maybe it's a few more steps. But once you can connect these two pieces, you then, since you have these and these already figured out, you'll have a complete synthesis. Now, this will be much more useful later in the course when we have more reactions. For now, we're really focused on the EAS reactions of benzene, so let's take a stab at this question. Feel free to pause the video and try to solve this synthesis problem. There also may be more than one solution, so the solution I find may be different than the one you get, but as long as you followed the rules and there were no deviations, it should be a correct synthesis. So let's take a look at how I might approach this problem. The first thing to notice is obviously that we've added two alkyl groups. Now notably, one of them is a methyl group, which I should have no problem using Friedel-Crafts alkylation to make. The problem is that this is a propyl group. And if you recall, trying to make this propyl group add onto a benzene using the alkylation won't work, as it'll form a primary carbocation, which will swiftly rearrange to a secondary. Catching that early may help you understand that we may need to use acylation followed by the Clemenson to get this kind of thing on my final product. So for FC acylation followed by Clemenson. Now, the one other and much more important thing to notice is that these groups have a meta relationship to each other, right? They are both meta to each other. The issue is that as they are in the final product, these groups are both activating groups. They're weakly activating, which means they would not want to be meta. They would be ortho-para-directing. Considering everything, let's take a stab at approaching this question, right? You might consider, well, let's add this alkyl group first. It seems easier. So we can consider that. By using the Friedel-Crafts alkylation, the methyl group can be installed. You'll quickly realize that this isn't a good strategy, though, because the next step is to use Friedel-Crafts acylation to add the acyl group. And if you were to do that, recall that any group you would add to toluene would want to add to the para position. That isn't what we want, and so that system isn't going to work. Instead, let's use the acylation first. We'll come in with the 3 carbons that we want. Make sure to count your carbons. 1, 2, 3. There we go. 1, 2, 3. No, 3 carbons isn't too many, but once you get to like 5, it's very easy to drop them. This will add the acyl group, and we'll draw it where we want it to go in the final product, up at the top. There we have our 3 carbons. Now the acyl group is a strongly deactivating group and a meta-director. The question is, where do we go from here? I could immediately go ahead and use the Clemenson to reduce it down to the alkane. Right? That removes the double bond, replaces it with hydrogen. Alternatively, I could come in and do the acylation, or rather the alkylation, right away. Which option do you think is better? Right? The answer is that the bottom option is better. Doing the Clemmensen right away, while it would get us the alkyl group that we want, I'm not sure why I changed the position of that alkyl group, we'll keep it up there. But the problem is, we would then have to do the alkylation. This is an activating orthopara group, and we wouldn't get that meta relationship. As you can see, synthesis problems they involve a bit of trial and error, right? You need to know your ABCs, but then you need to also understand how the ortho-meta paraselectivity is going to evolve throughout the reaction. Right? By using the acyl group, it is a meta-director, and we'll be able to get that alkyl group, that methyl group, where we want it. Lastly, we can come in with the zinc-mercury amalgam, the HCl aqueous, that's the Clemmensen reduction, and we can get our final product. So it's a three-step synthesis, but as you can see, there was a lot of places you could have gone wrong on this one. I'm not aware of any other strategy to make this, but if you found one, good for you. Just make sure that the ortho and para-directing groups and meta-directing groups all make sense. So that's the first synthesis problem. Let's take a look at the second. Now, this one looks a little bit more complicated, a bit going on. Let's take a look. Once again, we're starting with a naked benzene, and we have to make a pretty complicated thing. So what have we added to the benzene? Well, clearly, there's a chlorine, there's an NH2 group. Right? Now, the NH2 group, we know we actually can't add that directly, but we know that if we have an NO2 group, we can use the Clemmensen reduction to convert it to the NH2. Awesome. Last but not least, we have this whole big group. Right? Now, while this cyclohexane ring is scary, don't worry about that. The key idea is that we see a carbonyl here. That's an acyl group. This may as well just be R. Right? We have to use the Friedel-Crafts acylation to make it. So, again, thinking about how we can solve this question, sometimes guess and check is a good strategy. So let's just go ahead and add the chlorine. Why not? Right? For a question like this, there may be more than one correct answer, remember. So don't worry too much about finding the exact correct one and just start trying things. We can add the chlorine. I'll just put it in the position that we will want it in the final product. Again, it doesn't matter at this point in time. The chlorine is an ortho-para-directing group. So considering that the chlorine is a ortho-para-directing group, which group would I have to add next? Well, I'd have to add a group that is in one of the ortho or para positions. That's what chlorine would do. In this case, we have to add the NH2 group, and again, remember, we can't do that directly, but we can add the NO2 group. So the reagents to add the NO2 group to the para position, try to pause the video and remember what they are if you forgot. Right? The NO2 group going para, that's going to help us, and I guess you should draw the N directly connected to the benzene. This would be HNO3 in the presence of sulfuric acid. Excellent. So now we have a couple options. One option is to add the acyl group directly. If we add the acyl group directly, right, where would it go? Well, we have two substituents, so let's quickly take a second to make sure we know where the directing groups are going. Right, the nitro is a very strong deactivator, and the chlorine is a weak deactivator. Now, this benzene, considering that, is very unreactive, but let's just assume that we can get it to react for the purposes of this question. We would listen to the chlorine, right? The chlorine is the least worst. It's the most activating thing by not being as bad as the nitro group. So in that case, we would want to put the next group here or here, right? Well, wait a minute. That doesn't work, right? We need that next group to go to this position. That's what we want. So how can we do that, right? Well, luckily, you may have realized that the NO2 group still needs to turn into the NH2 group, and the NH2 group is a strong activator. We can do that by using the Clemmensen reduction. Now that we have our NH2 on the ring, that is a strong activator, and it's far stronger than the chlorine. So pay attention to how these post-EAS reactions, these things you can modify, can significantly change the reactivity of your ring. Note that this molecule would not be very reactive in EAS reactions whatsoever, but it could absolutely react with the Clemenson. And this ring is very active. The NH2 is a strong activator. Now that we have both an activator and the correct selectivity, we can do the Friedel-Crafts acylation. Okay, pay attention that this carbon here should be this carbon here, and make sure that you don't lose any carbons when you add the R group to your structure. Don't forget the Lewis acid catalyst, FeBr3, and you would get your final product in a total of 4 steps. So while these questions are a lot harder than the roadmap questions, you're typically given a lot more time to think about them. Hopefully you found these work-along examples helpful. Feel free to try the practice problems below. And that's the end of the Reactions of Aromatic Systems chapter. I'll see you in section 5, where we'll start talking about carbonyls. And by the end of this course, you'll see that we can do a lot of things with carbonyls. I'll see you then.